Hi everyone, my name is Olivier RENAULT and I'm in charge of the surface analysis laboratory at the platform for nanocharacterization of leti, a technology institute located at CA in Grenoble, France. And I'm happy to give you now a flavor of what I will be hopefully presenting you in live mode next year during the FPWS workshop. My talk is about the new paradigm of 2D materials as revealed by momentum microscopy. We are talking here about laboratory-based momentum microscopy. The needs for imaging are widespread. You have some examples on the left regarding test areas and wafers, because this is the field we are dealing with at leti. Microsystems and nano devices are also have also high needs for imaging. In most of the cases, high lateral resolution capabilities are required. This is also the case for 2D materials and related heterostructures. This class of material is fairly new, especially so-called transition metal dichalcogenides, for which you have an illustration of the atomic structure on the right. These materials kind of, so to speak, follow the advent of graphene 15 years ago and are made of a layered arrangement of transition metals such as molybdenum, tungsten, tantalum, and sulfur, selenium, or tellurium atoms. These have fascinating properties regarding the bond structure, because there is actually a transition from bulk to the monolayer form, where the bond gap becomes direct in the monolayer form as opposed to the indirect bond gap of the bulk form. So for these materials, high need of bond structure data, but over well-controlled areas, and this is because these areas can be fairly small, so you need to perfectly control your analysis area in order to get meaningful data. The instrumentation we are using for these studies is a NanoESCA instrument, which has two capabilities. It has a capability in momentum microscopy using so-called HIS-14 source, which is an helium source, which has been tailored especially to provide a microspot on the sample, and the illumination is under grazing incidence, which is very useful in the study of 2D materials such as TMDCs. Besides momentum microscopy, we are able to perform core level microscopy using monochromatic X-rays, which is some kind of unique and again quite critical in some cases for looking at 2D materials. In the inset of the photograph, you have a closer look at the source, which is a pretty long arm, because at the end you have this focusing optics represented in the picture on the left, which focuses the helium spot into a spot which has typically a footprint of 500 to 600 microns in the sample, and which enables to concentrate the photon flux in the microscope field of view. So the first example of bond structure study using this instrument deals with molybdenum diselenide graphene heterostructures, where you have one PNIM image is represented on the right. You have the molybdenum diselenide, which has been partially deposited onto graphene itself, being layered onto silicon carbide. And the beauty of the NanoESCA instrument is that you can very easily switch from direct space mode, this is the PIM image on the right, to angular space mode, where you select basically a restricted area, in that case something like 18 microns. You select such an area on the field of view of the PIM image, and you can record the angular images, which translates into momentum images basically. And you have a perfect control over this area which you are selecting. So you have two examples of bond structures. One on the bare graphene, when you can recognize very easily the set of direct cone at the rim of the field of view, and the bond structure on the heterostructures, the red one, where you have the intense gamma bond at the center of the field of view and all around the K and K prime point, which play a very important role in the electronic properties. So when you actually play the whole bond structure experiment, you will see the graphene bonds appearing on first, and then in the middle, the bond coming from the molybdenum diselenide are clearly visible. And out of this data, you can make a cut over particular high symmetry direction, and you can derive the bond structure data. So bond structure analysis helps you accessing crucial physical data. And I will be illustrating this by a study that has been published some years ago. This is the work we've performed together with EPFL, Professor Andraskis, on molybdenum disulfide layers deposited onto sapphire. So a heavily insulating substrate. This is an interesting study because it tells you that such an analysis using kPEEM, momentum microscopy, is feasible even in the case of heavily insulating substrates. And this is because we did deposit actually a metallic film partially covering the molybdenum disulfide, and that we could analyze such material on an area closer to this metallic film. So this is very quickly some K-space images where you on the last one you can see the main point of the reciprocal space of interest. By performing a cut along this high symmetry direction, you can retrieve the bond structure, which is in that case quite normal. Especially you have the K point located above the gamma point, and you can extract from each of the bonds some crucial parameters, such as, for example, the effective mass of the carrier of the holes at K and at gamma, and compare with literature. So this is what we did, and we found some hole effective masses at gamma which were matching the data for unstrained molybdenum diselenide derived from density functional theory calculations. And besides this key physical parameter of the hole effective mass, we can also derive the in-plane lattice parameters simply by measuring the gamma K distance in on the bond structure, which helps deriving the in-plane lattice parameter. And what we see in this particular case is that the in-plane lattice parameter, as seen from the gamma K distance, is very close to the bulk value. And this tells us that in this case of this particular case of van der Waals epitaxy of the molybdenum disulfide, we have a nearly quasi-freestanding crystals sitting on the substrate. The last example I wanted to mention is illustrating how bond structure data can validate cleaning processes. So this is an application which is less fundamental, so to speak. Cleaning processes of 2D materials are extremely important, especially in the case of graphene, which needs to be transferred from the substrate on which it is grown to a technological substrate. And to do that, we use most of the time a polymer in the form of PMMA, which needs to be removed totally from the graphene surface after the transfer process. So step number 3 is actually the transfer process of such a graphene after partial PMMA cleaning, but there is still some PMMA residue. This is what we've been showing. And the last step of the cleaning process actually involves plasma cleaning, using in that particular case a combination of CF4 and hydrogen gases, which helps removing the PMMA-G, so to speak, so a form of PMMA which is actually layered at the surface of the graphene and which is extremely difficult to remove chemically. So we've been implementing those plasma processes and optimizing those plasma processes in order to remove such PMMA-G. And we were wondering the influence of these plasma processes on the graphene itself. Do we have a graphene which is still technologically available, usable, meaning did we conserve the electronic properties of the graphene after plasma treatment? And kPEEM, momentum microscopy, is actually the only technique capable of telling this, evidencing this. And so this is illustrated on the left. You have a bond structure of graphene after plasma cleaning, which actually shows a multiple collection of direct cones. But this is because our graphene in this particular case is polycrystalline, so you have disorientation, in-plane disorientation. But we were able to extract the bond structure and see that the direct cone is actually shifted as a negative energy shift related to the Fermi level, which indicates end-doping. And this is a trace of the influence of hydrogen being trapped into the structure from the plasma. Nevertheless, the fact that we have a bond structure evidence that the graphene has been kept, maintained, untouched, nearly untouched after the cleaning process. So through these three examples, I wanted to give you a flavor of what I will be presenting to you in more details, and I thank you for your attention and hopefully see you next year.